Okay, so I hope I'm audible and okay, let's wait for 2 more minutes, then we can start. Okay, so I think we can start and maybe the students can join along the way. It's completely fine. So let us start. Okay, so welcome back to week 6 of the problem solving session for the Introduction to Fluid Mechanics course, and once again we will continue our discussion on fluid kinematics. So last week we started our discussion on fluid kinematics with the three flow visualization methods using streamlines, streak lines and path lines. We also discussed about uh, timelines, but we again emphasized that the major uh, content or major uh, for the majority of the things, this it is streamlines, streak lines and path lines that are considered to be the major flow visualization techniques. Okay, and now we will just continue our or proceed further with our discussion on fluid kinematics. So in this week's session, we will discuss about angular deformation, stream functions and velocity potential. Okay, again few of the other important aspects of fluid kinematics, and more or less again quite helpful in visualizing the flow. Okay, as I mentioned, for fluid kinematics we are more concerned with the motion of the fluid, and say if you are just tracing some particles, we are more concerned on how these particles will move around say a bluff body and will help us to visualize the flow around the bluff bodies. And we find some mathematical relations to find analytical expressions for these kind of patterns of the flow around some block bodies, or even just a flow like an ordinary flow as well. Okay, so I think for beginners like who are just starting the course, it might be a bit difficult to understand and visualize it in a best way possible, and unfortunately again I apologize that for the shortage of time or the limitation of time and the scope of the problem solving session, I am not able to show you some flow visualization techniques. But uh, I think it's upon the interest on the students who can dig deep a bit more and look upon some say even some YouTube videos that show this kind of flow visualizations. Okay, and I think in the lectures Professor Chakraborty has shown some of the flow visualizations in the lectures. So I think if the students emphasize a bit more on the sessions, and if they have attended it carefully, they would have understood the gist of understanding or getting to know about this flow kinematics or fluid kinematics in the grand scheme of things with respect to fluid mechanics. Okay, so with that, let us continue our discussion. Okay, so if you recall, in the last session we discussed about linear deformation. So we will just look upon the angular deformation again. We will look upon angular deformation in this session, but just as the previous sessions, I will not dig deep or dive deep into each and every concept that were discussed by Professor Chakraborty. for the sake of saving time and emphasizing more upon the problem solving aspect, I will briefly go through the concepts that were discussed, as it has been followed from the very beginning of the course. I'll go through briefly each and every topic that were discussed. If there's any doubt, you can ask. Of course, you can stop me anytime. You can ask me, and I will try to clarify it. But if I'm not able to clarify it, you can do two things. First, you can just maybe go back to the lectures. I think one way or another you will get the hint of how to solve it or how to tackle that problem. Or you can put that doubt in discussion forum. Professor Chakraborty or me will just try to tackle it out. The second option is you can just kindly wait, so that if the doubt is, I must say, quite relevant enough and important enough, I will take that doubt in the next session, clarify that in the next session, and I think that would be again a good way to handle these things. Okay. So let us proceed further. Okay. So we start with the integral form of the continuity equation. Okay. Now you may ask why we need to study integral form. Okay. So the thing is, the continuity equation that we have discussed in the last week was in the differential form. You can see there are differential operators operating upon flow parameters such as density and velocity. Okay, and in some way it's very important to understand the derivation and will eventually help us to derive the governing equations for fluid mechanics, that is in Navier-Stokes. Okay, so differential form is very important in that perspective. Again, it's upon the utility, it's upon the way of utility or the type of utility that determines which form of the governing equation would be quite useful to us. Okay, in some aspect or in some ways the differential form is useful. Okay, for example, if you're say doing CFD simulations and if you're doing some finite difference methods, the differential form of the governing equation is what that you handle while modeling or creating the code for your finite difference scheme. But again, if you're going for finite volume methods, which is the more general, I won't say more general, but I would say more commercially used in different kind of commercial software such as ANSYS, OpenFOAM, which uses these finite volume methods to solve the flow governing equations in the flow domain. And those equations, by the name, if you can understand, finite volume scheme would mean that they are integrating the equation over the entire grid element or the volume to solve these governing equations. So when integration gets involved, we are more or less aligned towards the integral form. Okay, so this is the differential form, and you will eventually see when we reach week 9, when we start the Reynolds transport theorem, we will see that more or less we will try to again revert back to our integral form of governing equations, and then we will start to solve fluid flow problems. So nevertheless, you'll see that for at least for today's discussion, one or few examples might involve the use of the integral form of the continuity equation. So that's why we'll look into it. Okay, so we take a very specific case. Again, this was discussed already in the class, but we take a very specific case of a steady flow. I'm not saying incompressible flow, but I'm saying a steady flow. So for 1D steady flow, this equation will reduce to this form. Okay, only one velocity component and only one derivative along the x direction. The unsteady part will get removed. Then if you just integrate the equation over the volume, and you may ask what this volume is. So this volume would be the volume of your control volume. Okay, so then if you integrate it, so now if you just convert this equation in vector notation, you can write this equation as such. Okay, that divergence of rho u I cap dv, the volume integral of divergence of rho u I cap dv would be equal to 0. It's the integral form of your continuity equation for a 1D steady flow. Okay, now you may ask how we reached here. Okay, so again, it's a very simple manipulation that was discussed or derived from the Gauss divergence theorem, where we convert a surface integral to a volume integral by using this relation. Okay, and again vice versa, you can again convert this volume integral to a surface integral, and you will see eventually that depending upon the problem, at least for solving finite control volume problems using the control volume method, you will eventually have to use the Gauss divergence theorem to convert your governing equations to a from control volume to a control surface integral. Okay, that's what we have to do, and we'll eventually see one example. We'll shortly discuss it. But for the sake of better understanding, I think you can do a bit of homework. That is, you can look into these three theorems and just to understand what the derivations actually mean. Okay, so here we have discussed the Gauss divergence theorem. So similarly, we will also see, I am not sure whether we will discuss it or not, but we will also see that Stokes theorem also turns out to be quite useful while discussing the fluid kinematics problems. So Stokes theorem might also be useful where it converts a line integral to a surface integral. Okay, and the specialized version of the Stokes theorem is the Green's theorem. Again, Green's theorem, don't get confused with the Green's theorem for solving differential equations, but again it's a specialized case of the Stokes theorem where the problems we simplify to 2D scenario. Okay, so you might look into these three theorems for your proper revision, and maybe then you will understand the equations and how the manipulations have been made to solve the problems. Okay, so for a simplified case, consider that the velocity, say, or I would say this, say a vector f is equal to rho u I cap. Okay, density times the velocity. Okay, then consider that this is the control volume that we have considered, which is basically a nozzle, again a subsonic nozzle, where ideally the velocity will increase as the area reduces in the flow from the left to the right direction. Okay, as the area is reduced from the continued equation, you can easily say that the velocity will go up as the area has been reduced. Okay, so we'll consider a similar example that we have discussed very thoroughly in the previous class. So if you apply this integral here in this equation, again f here is the vector rho u I cap. Okay, so if you just apply this scenario here, you will have something like the volume integral of nebula dot rho u I cap dv is equal to the surface integral of rho u I cap dot n cap dA. Okay, now n cap here will be the normal vector of the area of the inlet and the outlet. Okay, so since there are two areas, it is one area at the inlet and one area at the outlet, you need to apply this equation at both this inlet and outlet. Okay, and again depending upon the formula, if there are multiple inlets and multiple outlets, you basically this integral becomes some kind of summation where you sum up some of the contributions of all these type of flows across the inlets and the outlets, and look upon the net change in this integral. Okay, again for steady flow, this will turn out to be that the net influx would be equal to net outflux, but you need to again formally derive it to properly understand the problem. Okay, and depending upon this identity, that for steady flows the inlet would be mass influx will be equal to the moment mass outflux or mass efflux, you might that relation might become useful for solving different kind of unknowns in the problem. Okay, so let us proceed. So here this equation will basically be integrated at the inlet and the outlet, or exit in this case. So here, since the normal vector of the area is in opposite direction to the vector of the velocity vector, that's why we will have n cap to be of minus I cap. Okay, similarly, since the flow is going out of the outlet and the normal vector of the area and the velocity vector are along the same direction, so we'll have this as positive I cap. So if you simplify this a bit further, you'll see that you will get something like area integral of rho u dA would be equal to area integral of rho u dA at the exit. Okay, and if you simplify it even further, if you just consider that the density is okay, you may not need to do it. You can simplify it in this form. Okay, there is rho I ai ui is equal to rho e ae u. Again, a simplified form of this equation. Okay, considering that even if the density is not constant, you will assume that this integration will give me something like rho e ae ue, where ue might be different from ui and rho e might be different from rho I. Okay, this might be different. Depending upon that, this at least this product would remain constant across the inlet and the outlet. Okay, and depending upon the requirement of the problem, you might be asked to find the desired parameter. Okay, so I hope this is clear till now. And if you see that this parameter, the density times area times velocity, is basically the mass flow rate. Okay, and if you just divide this by density, it will give you the volume flow rate. And now if you consider a simplified scenario, like a special case where density does not vary over the cross section, then you will have something like rho I integral of rho I times you can take this density out of the integral, or it will basically be rho I times integral of ai u dA, or this will give you something like rho I ui ai, exactly same as this one. Again, this again we consider that the density does not vary across the cross section, and we can have the, then we can formally define the average velocity as this ui or ui bar would basically is the average velocity across the cross section, which is the integral of u dA divided by the area of cross section. Okay, so this is the formal definition of average velocity across this cross sectional area at the exit or at the inlet. And the average velocity in a way is basically helps us to know like what's the order of magnitude of the velocity across the cross section. So it might happen that the velocity at the edges might be lower than the velocity at the center line, okay, because of no slip boundary condition, and you will see that eventually velocity profile turns out to be of this form, okay. But then also to get an average sense like how the what would be the magnitude of variation, or I must say what would the magnitude of the velocity across this exit, then this average velocity gives us a brief idea. Like say the velocity varies as 5 meter per second. I won't say that it is 5 meter per second across the entire cross sectional area, but more or less the order magnitude of velocity at that particular cross sectional area is around 5 meter per second. So this gives you a brief idea of how the velocity varies across the cross sectional area, and you will see that for many problems this will turn out to be very, very handy, okay. Then we again consider a further simplified case where we consider, say, the density is constant across the inlet and the outlet. So if the density is constant or it does not change, which is usually the case for many fluid flow problems where density variation is quite low, then we can just cancel out the density term. If you go back here from both the sides, then you will have something like aiui bar is equal to aiue bar, okay. And ui and ue are the average velocity across the cross-sectional area, and this equation again is sometimes very popularly known as the continuity equation, and this actually is the if you it's a very the integral from the continuity equation for constant density. Again, if I go back here, this can again be considered as an integral form of the continuity equation, okay. Again, considering that the density does not vary across the cross-sectional area, okay. So I hope this is clear till now, okay. Maybe I will wait for 1 minute. If there is any doubt, you can try to think it out and maybe ask me. So I'll wait for 1 minute, say still for 1 minute, and then we can start this example, okay. This example again was taken in the class, but just for recapitulation and a proper revision, I will discuss this problem. Okay, then if there is no doubt, let me proceed further. Okay, so this is the example that was taken by Professor Chakraborty in the class, just to show us the proper use of the integral form of the continuity equation for a given problem, okay. And again, this is an Eulerian approach to solve this kind of problem, where you can see that a rectangular disc or rectangular plate is being kept fixed at a particular location at a height h from the ground level, and which has a width of b and the length of l, okay. And the ground is not a impermeable ground, rather it's a porous media where velocity, there is a flow inlet across the pores in the ground, and this kind of ground where the flow can occur through these pores are always known as porous medium or a porous wall. And they have modeled the velocity at the through the porous media as something as a constant velocity inlet, with the velocity being equal to v naught, okay. So our task is to find first to find the velocity components u and v, uh, and the acceleration a across this exit, okay, or across this domain. What would be the flow velocity components and what will be the acceleration in this given flow domain? So to simplify the problem, since the geometry is symmetric and the flow is also symmetric, uh, we can divide this problem across the center line of the given geometry and consider that the flow, whatever the flow is here along this direction, would be the same across this direction. Okay, so the area of interest would be something like, along the x direction would be L by 2, along the y direction it will be B, and along the z direction it will be H. Okay, so now let us try to proceed further. Okay, so we again apply the two, since we are dealing with velocities, so you'll eventually see that when we solve the problems using Reynolds transport theorem, or the differential form, or the integral form of the governing equations, you will see that when there is a problem that is related to finding, say, velocity and acceleration. Of course, if you find velocity, you will eventually get the acceleration, but if you are concerned with finding the velocity components, the equation of interest becomes the continuity equation. Okay, because it gives, for if density is constant, then it gives us an explicit relation between the velocity components. And more or less, like for most of the problems, you know at least one of the velocity component. Okay, that simplifies the problem. So the other velocity component you can find using the these governing equations. Okay, which we will do the same thing here. And if there is a problem that is related with finding the force, the net force acting on the control volume, and for those kind of problems, the equation of interest becomes your momentum equation, because it gives us the rate of change of momentum, which is basically the force acting on the body. Okay, and you will see that these two equations are not explicit, rather they are interrelated to each other, where to find the parameters, unknown parameters for the momentum equation, you will have to explicitly solve the continuity equation. Okay, so there is a step by step method that has to be followed to completely solve this kind of problems, like in these problems in the basic fluid mechanics course. Okay, so yeah, let us proceed. So let us just try to understand first, like, what are the things that are unknown and that are needed to be found out. Okay, so since the flow is steady with constant density, the continuity equation reduces to this form. It is the integral form, of course. It is AIUI at the inlet is equal to AEUE at the exit. Okay, where UI and UE are the average velocities. And again, since the flow is inviscid, okay, it's already given that flow is inviscid and density is constant, then the velocity profile would be of a constant velocity. Okay, it will form a constant velocity profile since there is no shear across the walls, so the velocity would be a constant. The velocity profile would be of a constant velocity profile. Okay, it will remain constant across the cross sectional area. So from this equation, you have the area at the inlet, AI, would be the width, like here the area would be the width B times X. Okay, now you may ask, why not L by 2? Okay, the flow is still developing, that's why the flow is purging out of this rectangular plate. So it's not explicitly said that the flow is developed in a sense that the flow is completely out of the edges of the plate, so it's still developing, so it's not explicitly developed. So we assume that, let our control volume be of this form, where the area along the x-axis, the length across the x-axis is given by, say, something like x, but along the y and z direction it's fixed, because the plate is fixed at a distance of h from the ground and the width of the plate is b, so it is fixed. But along the x, since the flow is still developing, we'll say our control volume is this form, where the inlet velocity is across this area and the outlet velocity is across this area. Okay, the problem would have been much more difficult if we would have considered the viscous effects as well. Okay, but for simplified case, for these given scenarios, the problem has become a bit more simpler. And so Then for this control volume, the area at the inlet would be Bx, and the area at the velocity at the inlet would be V naught, because it's a constant velocity across the porous media. Similarly, at the outlet, the area at the outlet would be H times B. Okay, but velocity at the outlet is something that's unknown. That's what you need to find out. So UE would be function of x. Okay, it might vary across the axial direction, but there is no variation along the along the height, along the y-axis. Okay, so UE would be function of x. Okay, it might vary across the along the x direction. So you will have, from this equation we will have something like UEx would be equal to V naught Bx divided by Bh. So B and B will cancel out, so we will have UE as V naught x by h, and you can see that the x velocity component is indeed a function of x, even though the viscous effects are not there, but the flow might still vary, like the magnitude of flow might still vary along the x direction because of the developing condition of the flow. Okay, once the flow is being fully developed, it might not be a function of x. Now you have the x velocity component, that is u. Now what you need to do is you need to find the v velocity component, but this equation is again quite limited because there is no way to find the velocity component along the y direction. Okay, there is no explicit equation, and we have already used this equation to find the x velocity component. So now you may think what we can do further. Okay, so but still what you have is the continuity equation. If you remember the differential form, that is dou u by dou x plus dou v by dou y equal to 0, and given that the flow is steady and density is constant, the simplified form of the mass conservation or the continuity equation reduces this form. And if you remember, just for a recapitulation, this equation is varied for irrespective of the flow being steady or unsteady, because the density is constant. So your d rho by dt is equal to 0. So this term explicitly becomes 0 from the mass conservation. Okay, so just as a point of revision for you. Now from this equation, what you will have is, you already know u. So what you can do is you substitute the value of u in this equation. So you will get dou v by dou x would be equal to v naught by h plus dou v by dou y, or we will have dou v by dou y to be equal to minus v naught by h. Now if you integrate this equation, again this is a very important thing, like I think most of you might already know, but this is not a complete differential. Okay, it's a partial derivative or a partial differential equation, that is dou v by dou y equal to minus v naught by h. So now if you integrate it, instead of getting a integration constant like you would have got in the case of a ordinary differential equation, you will get a function of the other variable. So if you integrate with respect to y, you'll get something like, v is equal to minus v naught y by h, because v naught and y are constants, plus some function of x. Okay, and now what you need to do is you need to find this function of x, what it is. Okay, so maybe now you can use the boundary conditions. Okay, because at y equal to h, v equal to 0, from the no penetration boundary condition, that there is no flow across this plate. So you have a valid boundary condition that at y equal to h, v, or the v velocity component is equal to 0. Okay, so you will have v equal to 0, y at h, so minus v naught plus some function of x, or which gives us that this f of x is v naught. Okay, now you might again ask, why this f of x is equal to v naught and not some function of or identity of x? Again, some function of x can also be a constant. Okay, it's not invalid. A polynomial function also includes constant in its start, so it's fine. A function of x can also be a constant. Again, you can correlate it by understanding, like when you try to solve equations using the method of separation of variables, where you have one of the LHS and the RHS to be explicit a function of x and y respectively, like I'm just saying, and these explicit functions of x and y are again equated to be some constant. How this is valid? You can just now try to correlate that fact with this one. So if you substitute the value of f of x back in this relation, you will get v as v naught times 1 minus y by h. Okay, Now the second task was to find the value of acceleration. So again we will use the same equation for acceleration that we discussed so much in the previous class. So ax would be dou u by dou t plus u dou u by dou x plus v dou u by dou y. So you will have, since the flow is steady, u is equal to dou u by dou t is equal to 0. So we will have ax as u dou u by dou x plus v dou u by dou y. Again, since u, if you remember, u is v naught x by h is not a function of y, so this component will also be equal to 0. So we will have u dou u by dou x, so v naught x by h plus v naught by h, that is dou u by dou x. So we will have ax is equal to v naught square by h square. Similarly, you need to find the y acceleration component, that is ay. So you will have dou v by dou t. Again, since the flow is steady, dou v by dou t is equal to 0. I just neglected it. That is dou v by dou t would be equal to 0. So we have u dou v by dou x plus v dou v by dou y. Since v is again is a function of y only, if you see here, so you will have dou v by dou x to be equal to 0. So the only contribution that will be made will be the second term in the y acceleration along for the acceleration along the y direction. So we will have v as v naught 1 minus y by h, and the dou v by dou y will be equal to minus v naught by h. So if you simplify it, you will get ay is equal to minus v naught square times 1 minus y by h. Then you got the component, so a can be simply written as ax ik plus ay jk, where ax is this one and ay is this. Okay. So so Professor Chakraborty pointed out a very interesting fact of something that we were qualitatively discussing in the previous class, that the explicit demarcation between the local acceleration component and the convective acceleration component. So we said that this local acceleration arises because of the variation of the velocity components with respect to time. Okay, but we also said that because of the variation of the velocity along the spatial directions, since we are considering velocity function of both space and time in the ordinary approach, and because of the change in the spatial conditions, spatial conditions, the velocity might change with respect to space. So that gave rise to the convective acceleration components. So you can see that even though velocity components are not a function of time, we still get a non-zero acceleration, and this acceleration is again primarily contributed or explicitly contributed by the convective acceleration components. Okay. So again, I'll just wait for 2 minutes, just to again rest a bit for me as well. I'll rest a while, but you can just maybe try to recapitulate the discussion that we had till now. Maybe I'll just scroll back to the part that we have discussed, maybe the derivations. You can look into it. If there's any doubt, you might ask, and then we'll start with the angular deformation of fluid element. Okay. We'll just wait for 2 minutes, then we can resume our discussion. Okay, so I think we can proceed further. So there is no doubt, I think let's proceed further. Okay. So we resume our discussion with the angular deformation of the fluid element. So similar to the linear deformation, as we discussed, that the flow may elongate along the respective x, y, and z direction, which basically gives us the linear deformation, which was again quantified as epsilon xx dot as dou u by dou x, epsilon yy dot as dou u by dou y, and epsilon zz dot as dou u by dou z. So those relations gave us the linear deformation, and when we sum it up, it gave us the rate of change of volumetric deformation divided by the volume. Okay, that gave us that relation. But as I mentioned in the last class, and we also discussed it previously, the flow might also undergo angular deformation. Okay, because of the shear forces, and that again is quantified by using the shear strain components. Okay, so I will discuss the components, the final form, but for the sake of saving time, or for the sake of brevity of this session, I will not go through the entire detailed derivation. So it's very beautifully described or derived in the lecture by Professor Chakraborty, or I also in many standard textbooks they explicitly derive it. Basically, it's the rate of change of the angle between the two line elements. Okay, as it's mentioned here, which were initially perpendicular to each other. Okay, so that you find it then, considering a rectangular, of course a cubical fluid element, but just considering, say, along one face, we can consider the deformation, and just find the average rate of change of the angle between the two line elements, which were initially perpendicular to each other. Okay, so with that idea, you can derive these relations. Okay, but and it's a good practice to look into those derivations. This gives you a very good idea, at least as a beginner, of how this deformation, or how the basis of understanding the deformation was laid while developing this course. Okay, and you can again make similar arguments for different coordinate systems, say the spherical and the Cartesian coordinate system. But again, the idea will remain the same, but identity might change a bit depending upon the coordinate system. Okay, for example, dou u by dou theta, we know that the deformation of the these fluid elements have a dimension of velocity times times length, right? But if you do something like dou u by dou theta, say derivative the deformation along the theta direction for, say, cylindrical coordinate system, but theta is a non-dimensional quantity. So again, you will see that to normalize it, you have some parameters such as dou u by 1 by r dou u by dou theta, that basically normalizes this identity, which gives us a similar dimension, then it is velocity by length. Okay, so as an exercise or homework, you can maybe try to look into the similar identities for different coordinate systems. Okay, but for the sake of this session, I will limit our discussion to only Cartesian coordinate systems. Okay, so let us proceed further. So we see that the deformation, the strain rate tensor components are given as such. It is epsilon xy dot is equal to dou u by dou x plus dou u by dou y. Epsilon dot yz is equal to dou w by dou y plus dou u by dou z, and epsilon dot zx is equal to dou u by dou z plus dou w by dou x. So you'll see that there's a very simple. First of all, again, in many textbooks, these relations are sometimes multiplied by half. Okay, so depending upon the textbook or the author, the identities might have this factor of half. Okay, so maybe for I think for our course as well, we keep this factor of half. Okay, so let us just multiply this with half. Okay. Or maybe I think what would be better is to properly write it so that the confusion is removed. So something like this, and multiply this with half. Okay. But again, there might be some certain textbooks that they do not keep this factor of half. That's again completely standard, because the the parameter of interest is actually the velocity gradients rather than the factor of half. Okay, so you'll see that becomes eventually insignificant, and more or less the conceptual clarity is much more important than this factor of 1 by 2. Okay, but still, for avoiding confusion with these subjective type problems, which might vary with a factor of 0.5 with respect to different options. One option might be 1, one option will be 0.5. So the entire difference that arises might be because of this factor of half. Okay, so I don't want you to fall into that trap. So for this particular course, let us keep this factor of half. So what it is that, if you see, there is a very interesting pattern. Okay, I will come back to the index notation, which will eventually give you the proper idea. But still, then also you can see that if you have some component that is epsilon naught xy, that is the the strain rate tensor along the xy coordinates, you will have what you need to just do is just take the derivative of the velocity component with respect to the other coordinate direction. Okay, so if you are considering the derivative of the v velocity component or the y velocity component, take the derivative of the y velocity component with respect to x. Similarly, take the and add it with the derivative of the u velocity of the x velocity component with respect to y, and you do a similar thing for yz as well. If there is dou w, then you take the derivative with respect to y, not with z. Okay, similarly, if you're taking derivative of the y velocity component, take the derivative with respect to z. Okay, just interchange the coordinates of derivatives for the velocity components. Similar argument can be made for zx as well. There is dou u by dou z plus dou w by dou x. Okay, just an interchange of these coordinates. Okay, and the standard way to, or in the index notation for this particular thing, can be given as something like this, where epsilon ij dot tells us the, or basically gives us the strain rate tensor, which is half times dou ui dou xj plus dou uj plus by dou xi. So I and j just tells us these are the two different components. They can never be the same unless and until we explicitly defined I equal to j, which is basically the case in the case of normal components. It is if I and j are equal, we can write simply as epsilon ii as half times dou ui by dou xi plus dou ui by dou xi, which gives us dou ui by dou xi. Okay, same, that is the, if I and j are equal, this basically gives us the normal components. Okay, so I hope this is clear, and I do not think that's much confusing. And from this you can clearly see that the stress tensor, the rate of strain rate tensor, is actually a second order tensor which is symmetric. That is epsilon ij dot will be equal to epsilon ji dot. Okay, so if you interchange the I and j index in this equation, you will get the same thing. Okay, basically this denotes a symmetric tensor. And Newton's law of viscosity can also be written as in this form. Again, you will see that the factor of 2 has come here because we have considered a factor of half while defining this strain rate tensor. Okay, we will carry forward this discussion when we discuss about the dynamics of fluid flow or the fluid dynamics part. That's why I just want to be consistent with my notation, not to confuse you further. So if you consider this, if you want to represent this tensor for the Cartesian coordinate system, you will see that for 3D case there will be 3 components. So it will basically give you it's a 3D tensor, if 3-dimensional flow, which is a second order tensor. It will give you 9 components, right? So you will have epsilon ij, which will give you 9 components. For the Cartesian coordinate systems, this will be the basically be the stress tensor. Okay, you will see that components such as epsilon xy and epsilon yx are actually same. So these components and this component are equal, this and this component are equal, and this and this components are equal. So basically this shows that this is a symmetric tensor. You can simply, like, if you want to be very sure, just take the transpose of this tensor, you will see that you will get the same result. So these are symmetric tensors. Similarly, now we can define the angular velocity, which is the arithmetic mean of the angular velocities of two line elements originally perpendicular to each other. So if you do that, you will get something like omega ij is equal to half times dou ui by dou ui dou xj minus dou uj by dou xi. So it's very understandable that students might get confused with this relation. So you will just be sure, like just try to not mess it up. Okay, so the stress tensor will have a plus sign in between the velocity gradients, and angular velocity will have a negative sign, and this negative sign is actually what that makes this tensor a skew symmetric tensor. Okay, that is omega ij is equal to minus of omega j. Like if you take the transpose of this angular velocity tensor, you will get it will turn out to be negative of the original tensor. Okay, so again there is a very good simple identity, that is the general velocity gradient can be represented as the sum of a symmetric and a skew symmetric tensor. Okay. Again, similar to the matrix energy, where a matrix can always be represented as a sum of a symmetric and a skew symmetric matrix. Okay, so square matrix, of course, a square matrix. So we also now define vorticity, which is again more or less quite similar to the angular velocity, and sometimes usually there is not much difference, but again because of the factor that we chose to define the angular velocity, you will see that this vorticity is basically the curl of the velocity field. That is for a Cartesian coordinate, this would be the definition of curl. So ij, again for the other coordinates you can find it accordingly. You will have ij k cap would be take the cross product of del cross v, you will get something like I cap dou w by dou I minus dou w by dou v by dou z minus j k dou w by dou x minus dou u by dou z plus k k dou v by dou x minus dou u by dou y. And if you see, it will turn out to be twice the angular velocity. That vorticity will turn out to be twice of the angular velocity. Okay. So again, for a simplified case, let me just ask you, if the flow is 2D, what will be the case? Okay. So you will see that if the flow is 2D, only the z velocity component will remain. Only the z velocity component will remain, and these two will get cancelled out. So we will have only the angular velocity along the z direction, and these components will remain. Okay. So now we will start the final part of today's discussion, that is stream function and the velocity potential. And just for you to know that these discussions are very limited in a sense that half of our discussion, the major half of our discussion I try to dedicate to the problem solving part, or from the problem solving perspective, like what are the things that you need to know to solve problems that will be asked in your assignment and in your exam. But I think that should not be the motto or goal of understanding any course. Okay, any subject or any course that you study should be learned from the perspective of understanding the course in a better way and trying to implement it for your interest. If you are a mechanical engineer trying to pursue research, or your final year BTech project for fluid mechanics, depending on which is related to fluid mechanics, then you should approach the course from an idea of understanding in a much better way, and try to study beyond what is being discussed in the class, in the lectures, or in this problem solving session. Okay, you might see why I'm suddenly saying this, because the thing is, I feel personally that whatever I'm covering here, for say this important concepts like stream function and velocity potential, is very limited, and only applicable, I won't say applicable, only useful for solving basic elementary problems that is relevant to this particular course, or any elementary fluid mechanics problems. But in a grand scheme of things, the application of stream function is very very actually crucial and are the foundations of many highly advanced research problems. So to understand it in a better way or even in depth, which must be actually be the motto of every student attending this course, I will suggest that please revisit the lectures once. That are, I think, quite sufficient enough. But still, for further clarification, please go to some standard fluid mechanics textbook that define these important concepts very nicely. Okay, so that will give you a better understanding and will help you to learn the course in the ideal way. Okay, so with this, I think I will just wait for 1 minute, since I just want to rest my throat for a while, and then I will continue. Okay, so please, I will wait for 1 minute, then we can start. Okay, so I think we can start. So, stream function is, I think, very important, or I can say a very uh, important in a way that it gives you an alternate way to simplify or to solve 2D incompressible flows in a simplified manner. Okay, let us see why. Okay, again, the important emphasis is in these two words. Okay, in these two words, first is 2D, that is stream function is only and only applicable for 2D flows. Second, it is valid for only incompressible flows. Again, there is a star in the scenario that by definition we said is defined for incompressible flows, but for special cases or special type of questions, the examiner might ask, like, what would how the stream function could have been defined if the flow was compressible. Okay, then also there are ways to define it. That's why I don't want to explicitly say it's only defined for incompressible flows, but the very gist of it is that it is defined in a way so that the incompressibility condition is satisfied, which it is the mass conservation is satisfied. Okay, but still there might be scenarios where it can be changed. So I will say it's a conditional case. Okay, but if not explicitly mentioned, then you can say these two terms, that is 2D incompressible flows, are required for defining stream functions. Okay, that's the gist of it. For special cases, again, you might look into relevant problems or relevant texts that give you this kind of scenarios where it's also valid for compressible flows. So by definition, we define something like U is dou psi by dou y. There is a x velocity component is defined as dou psi by dou y, and v velocity component or the y velocity component is defined as dou psi by dou x. Okay, and psi here it is the stream function, which is a function of x and y. And as you can see here, I have just discussed it here, that this equation satisfies the mass conservation explicitly, because if you replace, we know that, I think I should write a first term as well to remove confusion. The readers might get confused. So you have dou e by dou x plus dou v by dou y, correct? So if you replace the expression for u with respect to the definition of stream function here, okay, and replace v in this equation, you will get that the definition of stream function satisfies the continuity equation automatically. Okay, that's why that's the way, I must say, the base of deriving the stream function. But in the textbook for this course, that is Introduction to Fluid Mechanics and Fluid Machines, I think there is a very good section that first starts by discussing the physical significance of stream function. We'll come to that briefly, and then shows us how the derivation becomes quite valid when we define a stream function. Okay. So you might want to go through it once for a better understanding. Okay, but let us still just try to proceed further and try to understand how it might be helpful in solving problems. So we have psi, that is the stream function, as function of x and y. Okay, so the complete derivative of psi, that is d psi, can be represented as dou psi by dou x dx plus dou psi by dou y dy, which is again a very simple definition of taking derivatives or finding complete derivatives from partial derivatives. Since we know that dou psi by dou x is minus v from this relation and dou psi by dou y is u, we replaced it here, so we'll get something like dou psi is minus v dx plus u dy. Okay, now if you consider a scenario where this stream function psi is a constant, that is then it would mean that dou psi is equal to 0. Sorry, d psi is equal to 0. Correct? Simple definition from the perspective of derivatives, like if a function is constant, then its derivative would be equal to 0. Or specifically in this case, the complete derivative is equal to 0. So we will have from this equation, you will have v dx is equal to u dy. And if you simplify it further, you will get something like dx by u is equal to dy by v. And interestingly enough, it resembles quite well to the equation of streamline, just missing the z velocity component, right? Sorry, it would be dz by w, right? It's missing the z velocity equation for z velocity component. Again, you know why? Because it's only valid for 2D flows. But if we would have considered the equation of streamline for 2D flows with only x and y velocity component, this is exactly the equation of streamline that we are dealing with. So now you can see that there is an explicit relation between streamline and stream functions, though they are not exactly the same, but there is a certain relation. There is a scenario or a special case where if the stream function is constant, for that a stream function is a constant along a streamline. Along a streamline, the stream function will be constant. So that's the explicit relation between the streamline and stream function. Though they are not the same, but there is a very subtle relationship between them that helps us to correlate them. Okay. So along the streamline, you will see that this psi has to be constant. So the stream function psi is constant along a streamline. Okay. The difference being is defined for only 2D incompressible flows. The stream functions are defined only for 2D incompressible flows, and streamline is defined for all types of flows. Okay. The second factor that I want to discuss was how these stream functions are used, or actually the physical significance of stream function is that they actually show that it is a quantifying parameter for flow rates across a 2D incompressible flow. Because in a way, that's the thing, like for understanding this subtle concept, you have to be well versed with the I think it will be a great deal if you just look into this textbook by Professor S.K. Som, Professor Gautam Biswas, and Professor Suman Chakraborty, that is Introduction to Fluid Mechanics and Fluid Machines. So there they very nicely discuss this physical significance of stream functions. Okay, so I'm not discussing it because I think that for now it's beyond the scope of this course, because it will not be explicitly asked in the exams. But still, I think it would be a great deal if you just look into that part. Okay, so the thing is, in a very simple words, stream functions can be used to quantify the flow rate across two streamlines for a 2D incompressible flow. That is, if Q2 and Q1 are the flow rates at these two different streamlines, then Q2 minus Q1 would basically give you the flow rate between these two streamlines. So Q2 minus Q1 divided by V gives you psi 2 minus psi 1. Okay, so basically, like, if you just consider this to be 1, then psi 2 minus psi 1 basically gives you the flow rate between these two streamlines. Okay, so now if psi 1 and psi 2 are equal, then there is no flow. Basically, there is no flow, then there is no flow across a streamline. Okay, if psi 2 and psi 1 are equal, then there is no flow across a streamline. Okay, so this, for now, you can take for granted that, just take me for my words, that there is no flow across a streamline, which will turn out to be very, very handy when we discuss very briefly about the boundary layer while solving the integral form of the governing equations. But for better understanding, I will just suggest that please go through that section in the textbook. That will give you a very nice understanding of like how the stream functions are used in a way to quantify the flow rate across the streamlines. Okay, I won't say across, flow rate in between the streamlines. Okay, so the last part of this discussion boils down to the velocity potential, which is again I'm really sorry, I think in all this thing I just skipped the part of why deal with stream functions. Okay, when this very, very limited to only 2D incompressible flows, why at all bother about defining another parameter, the stream function? So the thing is, say if you're given a 2D flow also, then also to explicitly solve for the velocity components and the pressure, you need to solve two coupled equations. That is, first is your continuity equation and your momentum equation. Okay, so you need to solve for these two equations. So of course it is solvable, but it's quite hectic because you're dealing with three independent variables, P, U and V. Okay, which is quite of a tedious task from the start. Okay, it's a very tedious task to do. So by defining stream function, what you do is you simplify your scenario very, very much. Like if you just look at the continuity equation, rather than dealing with two different variables, you only have to deal with one variable psi. So you will see that your governing equation boils down to a single your momentum equation will again just boil down to a single variable psi, which you can use to, like, once you know psi, you can easily find out the pressure P. And because since by the definition of psi the continuity equation is already solved, the only thing that you need to do to find is solve for is pressure and the stream function in the momentum equation. So that's what you only need to do. You will see that the equation will become much, much simpler because of the use of the stream function psi. I think this will become much more relevant when we just solve some problems. Okay, then it will be like for example, like to define a flow field, like how the flow varies, the functional form of the flow, instead of defining the velocity components, you can define a single function psi to show how the streamlines would vary. Okay, how the flow would vary. Okay, that's where the use of stream functions become very, very important. Second is again the velocity potential. So it's again with the same principle, that given that the flow is irrotational, we can, rather than dealing with three separate velocity components, we can simplify our analysis by dealing with only one variable, that is your velocity potential, that is phi in this case. Okay, so from the definition, for irrotational flows, we know that the vorticity has to be 0, that is del cross V, the curl of the velocity field has to be 0. Okay, and again this implies a conservative flow field where we can represent V as the gradient of some scalar function phi. Okay. And the same argument can also be made while by looking into the detailed version of the curl of the velocity field. Like for example, if del cross phi del cross v equal to 0, then you will have this each components of the curl of the velocity field to be equal to 0. So we will have dou w by dou y equal to dou v by dou z, dou w by dou x is equal to dou u by dou z, and dou v by dou x is equal to dou u by dou y. Okay, so any function that satisfies these three equation should satisfy the irrotationality condition. So you'll see that if you replace w by something like dou phi by dou z and v by dou phi by dou y, you'll see that this equation is satisfied. Just write it for you. Like you just replace it with something like w to be equal to dou phi by dou y and u to be equal to it's dou phi by dou z actually, and v to be equal to dou phi by dou y. So this equation will be, considering that this function is smooth enough, like there's no problem with this function, it's a nice behaving function, then we will have something like dou square phi dou y dou z, or actually it should be dou z dou y minus dou square phi by dou y dou z. So if the function is smooth enough, then the order of derivative should not matter, so it will be equal to 0. Similarly, if you do the same thing, just define u as dou phi by dou x, these three equations will be satisfied. So that's again the way you can just say how the velocity potential can be defined. But using this relation also, like if a velocity field is irrotational, then you can represent it as a gradient of a scalar function phi. With this also you can represent this, that is u would be equal to dou phi by dou x, v equal to dou phi by dou y, w is equal to dou phi by dou z. This is basically the components of the gradient of the function phi. Okay, so this is how you define the velocity field. Again, the problem is simplified if you just have to deal with one unknown variable rather than two unknown variables or three unknown variables, because velocity potential can also be defined for 3D velocity fields. Okay, so I hope it is clear till now. Again, I will just take a break for 1 minute and then I will continue. Okay, so I will wait for 1 minute. If you have any doubt in between, you can ask me, no problem. And we just have the final part of today's discussion, like finding the relation between phi and psi, and then we can just start with the problems, so solving some problems. Okay. Okay, then I think we can proceed further. So what we'll do is, now let us consider a case where the flow is 2D incompressible and irrotational as well. Okay, let us consider that scenario. So we have d phi as, if we consider a 2D flow, so phi will only be a function of x and y. It's not explicit that it should only be a function of x and y, because it's valid for 3D flows as well, but we are considering a scenario where the flow is 2D incompressible and irrotational. Okay, so we are considering these three assumptions simultaneously. Okay, so we'll have d phi, that is would be equal to dou phi by dou x times dx plus dou phi by dou y dy. Okay, so we'll have d phi as u dx plus v dy, and for phi equal to constant we'll have d phi equal to 0. So from that, if you just simplify this equation, you will get something like dy by dx for phi equal to constant is equal to minus u by v. Okay, just consider equation, say just equation number 1. Now we know that d psi is equal to minus v dx plus u dy. Just to remove confusion, again both are same only, but still students might get confused, so I will just stick with my original definition. Okay, so for psi equal to constant, we have d psi equal to 0, or dy by dx would be equal to v by u. Say equation number 2. From 1 and 2, like if you consider multiply the slope of the flows with with constant phi and constant psi, you will get dy by dx, and just to reiterate, dy by dx basically shows the slope of that constant phi curve. Okay, similarly dy by dx gives you slope of the constant psi curve, the constant stream function curve, the curve with the constant stream function. So if you just multiply these two slopes, you will get something like minus u by v times v by u, or equal to minus 1, given that u and v are not equal to 0. So it tells us that since the slope of these two curves are equal, the product of the slope of these two curves are equal to minus 1, it basically implies that these two curves are perpendicular to each other, except at the stagnation points where u and v are equal to 0. Okay, so streamlines and lines of constant velocity potential are perpendicular to each other in the flow, except at the stagnation points. Or the correct way to put it would be that lines of constant psi and constant phi are perpendicular to each other in the flow except at the stagnation points. Okay, so stagnation points are the points where the velocity is equal to 0. By velocity equal to 0, I mean that all the components is equal to 0. So it will mean the velocity vector v is equal to 0, which would imply u comma v comma w to be equal to 0. So we know that u is dou phi by dou x and v equal to dou phi by dou y for a irrotational flow. So now if we impose this condition along, that if we consider this irrotational flow also satisfies incompressibility, I must have written incompressibility, right? So if this irrotational flow also satisfies incompressibility, then it will mean that dou u by dou x plus dou v by dou y should be equal to 0. Now if we substitute the value of u and v in this equation, you will get dou square phi by dou y, dou square phi by dou x square plus dou square phi by dou y square is equal to 0, which will basically give you that the Laplacian, this operator, this Nebula square operator, is also known as Laplacian operator. So Laplacian of phi is equal to 0. Okay, I think I should just write it. Maybe once you get the notes, you will be and similarly, now we also know that for from the definition of stream functions, you have u is equal to dou psi by dou y and v equal to minus dou psi by dou x. And if this scenario, if these stream functions, this which will imply that the flow is incompressible, also satisfy the irrotationality condition, then we will have the vorticity or the along the z direction, that is dou u by dou y minus dou u by dou x will be equal to 0, or we will have dou square psi plus dou x square plus dou square psi by dou square psi by dou x square plus dou square psi by dou y square will be equal to 0, or the Laplacian of psi, the stream function, will be equal to 0. Okay, so what it means that for a 2D incompressible and irrotational flow, both psi and phi satisfy the Laplace equation. Okay, and though the governing equations are the same, the solution of phi and psi would be different because the boundary conditions for these two functions will also be different. Okay, because they're defined in a different way, so the boundary conditions will also be different. Okay, so I hope so that's all for today's theoretical discussion part. So I will wait for 2 minutes for any kind of clarification required. Then I will start with a simple example as it is shown here. I will just start with a simple example and then I will start with the Q&A part for today's discussion. Okay, I will wait for 2 minutes, then we will start our discussion. Okay. Okay, so I think then we can start our discussion and solve some problems that are relevant to this discussion. So given that our velocity field is defined by v is equal to 2x I cap minus y j cap, so we'll have the strain rate tensor epsilon xy would be half dou u by dou y plus half times dou u by dou y plus dou v by dou x. Dou u by dou y would be equal to 0 because it's only a function of x, so this is 0. Dou v by dou y, dou v by dou x will be equal to 0, so we'll have epsilon xy equal to 0. You understand, right, why we are only considering epsilon xy? Because the w velocity component is equal to 0, and since the flow is 2D, there will be no variation of the velocity field across the third direction. There is no point of discussing that. It does not make any sense. Like, if there is no third direction, then why the flow would have a variation along the third direction, right? Along the third coordinate direction. It does not make any sense. That's why we are not considering the other strain rate tensor components. Okay. Similarly, and it does not. What I mean is that the flow being 2D mean that there will only be two velocity components that will be relevant. Okay. That's why the variation along third direction is not considered. Okay. Because you will see that if there is a variation along the third direction, eventually then the continuity equation won't be satisfied. So then you have to again frame it differently. Okay. That's why you will see that the flow will eventually become 3D. Even if like there's two components and there is a variation along the third direction of these two velocity components, then the continuity equation won't be satisfied. So we have to see like the flow, the entire fluid flow problem would be have to be changed accordingly. So we have wz, that is the not w, omega z as half of dou v by dou x minus dou v by dou y. So again, since dou v by dou x is equal to 0 and dou v by dou y is equal to 0, so we have that the flow is irrotational as well. Okay, so these type of flows that are incompressible, like as well as irrotational, are also known as dilatational flow, if I'm not wrong. Okay, so let us now take some relevant problems. Maybe you can help me out. So these problems are very simple, so I'll give you 2 minutes each problem, and then we can look into the solution. Okay, so it's again very simple. We have a two-dimensional velocity field, that is 2x I cap plus 2y square minus x square j cap. The rate of angular deformation, that is epsilon xy, and vorticity has to be found. Okay, so which of the following relations are true? Okay, so I'll give you say 2 minutes to solve it, and then we can proceed. Okay, so I think we have enough time. So it's actually very simple. So let us just look at the solution. I can solve it here as well, but since I've already created the solutions, so I think we can just revisit that. Okay, so we have v as 2x I cap as v as 2x I cap plus 2y square minus x square j cap. So rate of deformation, that is epsilon xy, would be half of dou v by dou y plus dou v by dou x. Dou v by dou y is 2x and dou v by dou x is minus 2x. So we have epsilon xy as 0. So flow is incompressible. Okay, and the omega z, that is the irrotationality part, will have dou v by dou x minus dou v by dou y, where dou v by dou x is minus 2x and dou v by dou y is again here, sorry, dou v by dou x is minus 2x and dou v by dou y is 2x, so minus 2x minus 2x equal to minus 4x. So this, since this is non-zero, given that x is not zero in general, like in the domain wherever x equal to 0, at that point the flow is irrotational. But since it is not given to find the irrotationality at a particular point, that's why across the flow domain, since across entire flow domain, to read flow domain, x cannot be equal to 0, so for the entirety of the flow domain, except at x equal to 0, the flow is irrotational. Okay, so our answer would be epsilon xy equal to 0 and epsilon omega z is equal to minus 4x. So option C is the correct one. Okay, so let us look at question number 2, which have a two-dimensional flow in the xy plane is irrotational if the u and v velocity components along x and y directions are respectively what? Okay, so this question is very simple. So I think since there are very few students, I will just take this question directly. Maybe you can spare some time on question number 3. So what we have is that since the flow is irrotational in the xy plane, so it would mean that omega z, this is again capital omega, so this is known as small omega, this is capital omega. Okay, I think I should have more like this one. Okay, so we have dou v by dou x minus dou u by dou y. Okay, if I'm not wrong, this must be the order. Yes, that's correct. I think this is correct. Yeah. So we have this would be equal to 0. So this will imply that for this to be equal to 0, these components has to be equal to 0. Correct? So we will have dou v by dou x should be equal to dou v by dou y. Okay. Very, very simple. Whichever it is, option number C. Okay. Option number C is the correct option. Okay. Now maybe you can look into question number 3. Okay. Maybe I will zoom. You can zoom out a bit. Yeah, that would be good. Yes, this is fine, I guess. So a two-dimensional velocity field is given by ay minus ay I k plus ax j k, where a is a dimensional constant. The field element in the above velocity undergoes. Okay, these are the options. It's only rotation without linear and shear deformations. Rotation and linear deformation in absence of shear deformation. Only shear deformation without rotation and linear deformations, and linear and shear deformations without rotation. So once again, since there are very few students, so I will give 1 minute to sort it out, and then we can maybe discuss the answer, because there are very few students. So anyone who will be watching the recordings, maybe pause the video here and then try to solve your answers yourselves, and then try to compare your answer with my solution. Okay, so wait for 1 minute and then you can maybe look into the solution. Okay, so I think we have enough. Maybe we can look into the solution. I'm sorry for rushing a bit, but it seems that since there are very few students, it's just better that maybe we can watch the recording later to see the solution. So whoever is watching the recording might just pause the video here for a while and then try to solve the question yourself. Very simple again, and then maybe try to correlate with the answer that I will eventually show now. Okay, and maybe we will follow this for the remaining questions. Since there are very few participants today, I think that would be a better approach for everyone. Okay, so let us look into it. Okay, so we have, so this is the velocity field, that is v is equal to minus ay I cap plus ax j cap. So omega z would be dou v by dou x minus dou u by dou y. So dou v by dou x is a, okay, and dou u by dou y is minus a. So a minus of minus a would be a plus a, that is 2a. So the flow is rotational. Okay, now angular deformation epsilon xy is half of dou u by dou x plus dou u by dou x, dou u by dou y plus dou u by dou x. So you'll have half times dou u by dou y is minus a plus dou v by dou x is plus a. So this will give you 0. So you'll have no shear deformation. Then for the linear deformation, we need to look into the normal components of the stress tensor or the strain rate tensor. I sometimes interchange between stress and shear strain rate tensor, because the only is for Newtonian fluids is just a factor of multiplying with 2 mu. Okay, so basically they are the same, just have to be multiplied by 2 mu. Okay, so we will have epsilon xx as dou by dou x, that is equal to 0, and epsilon y as dou by dou y to be equal to 0. So there is no linear deformation. Okay, so this is, so the flow is rotational with no shear deformation and no linear deformation. So the answer would be only rotation without any linear and shear deformation. So option A would be the correct answer. Okay, so let us now look into question number 4. That is, the velocity field in a fluid medium is given by x minus 4y I cap minus y plus 4x j cap. So again, you need to find the same thing, okay, whether the flow is rotational or rotational. So I think maybe I can just, since the pattern is quite similar, maybe I think we can just I can just solve it now and maybe you can compare it later. Okay, so we have, I will just show it here, it will be better. So u is x minus 4y, v is minus y minus 4x from this. So dou u by dou x plus dou v by dou y, let us check. Dou u by dou x is 1, dou u by dou y is minus 1, so it is, oh yes, so it is minus 1, so it is irrotational. Okay, the flow is irrotational. Now for the, sorry, the flow is incompressible. I'm extremely sorry. Dou u by dou x plus dou y equal to 0, so it means that the flow is incompressible. Okay, so option C and D are incorrect, so it's between option A and B. So now for the rotationality, let us check omega z, that is dou v by dou y minus dou u by dou x. So dou v by dou y is, I am again sorry, I have to change the derivatives. Dou v by dou x minus dou v by dou y. If I am incorrect, you should correct me. So we have dou v by dou x as minus 4 and dou v by dou y is, dou u by dou y is again minus 4. Okay, so you can see that this will basically be minus 4 plus 4 to equal to 0, so it will mean that the flow is irrotational. So the correct answer would be option number B, that is flow is incompressible and irrotational. Okay, dou v by dou x is minus 4, correct, and dou u by dou y, it's again minus 4, so minus 4 minus minus 4 is minus 4 plus 4 is equal to 0. Okay, flow is incompressible and irrotational. Okay, so let's look at question number 5, which is something new, that is a two-dimensional velocity field is given by x plus I cap plus x plus y I cap plus x minus y j cap. So here given the u velocity component and the v velocity component. Okay, so from that you need to find the expression for the stream function psi. Okay, so I will just solve it since there are very few viewers, so I will just solve it. You can pause it the video for now while you are solving it, and then compare it with my results. Okay, so you will have this one, right? So you have u is equal to dou psi by dou y and v is equal to minus dou psi by dou x from definition of stream function. Okay, so we'll have x plus y is equal to dou psi by dou y and minus of x minus y as dou psi by dou x. Now if you integrate these two functions, you will get psi as xy times y square by 2 plus some function of x, because these are partial differential equations, and psi, from integrating this equation, you will have psi as minus x square by 2 plus xy plus some function of y. Okay, now the thing is, since these two are the same functions, right, we are solving for the same function psi, then what you need to do is compare these two functions. So this is the tricky part. Integration is very simple actually, but the tricky part is, of course, if they give something like ex cos y, this thing again it becomes complicated. But for simple linear functions, the integration is quite simple. So you get, just need to compare these two functions. Now the comparison one is a bit difficult. So here if you look at this and this, so it says that x, y and y square by 2 would be there, but there will be some function of x. So if you look into it, like here y square by 2 is missing, which might be included in some function of y here, but minus x square by 2 is something new that is not here, and this is actually what the function of x that actually meant. Similarly, if you look into this, like from this, if you want to just compare it with this one, then you will have like minus x square by 2 and xy, but f of y, something like f of y is, xy is there, but an explicit function of y is not there, so it must be this y square by 2. So what you do is, whatever is missing, just add it in this function, or whatever is missing from here, add it from this function. Okay, I think it will come from practice, but I think you get it, what I wanted to say, right? Just compare these two functions. Whatever is missing would be the one that you have to add in the equation. So you will have, from this you will get psi xy is equal to y square minus x square by 2 plus xy plus some constant c. Okay. Again, just to revise, I think I was not able to make it quite clear or very quite fluid in your mind, but let us try it again. Okay. So let us first look into this expression. Okay, expression obtained by integrating this equation. So we have psi is xy plus y square plus some function of x that I don't know. Okay. Now I integrate this equation. I will get psi as minus x square by 2 plus xy plus some function of y. Now you see that xy is common in both, and since these two functions are same, these two functions has to be equal to each other. But there is minus x square by 2 here, and there is y square by 2 here, but it says that from this relation there has to be some function of x, and this again also says that there has to be a function of y. So if you just compare these two functions, then you will eventually see that this some function of f of x is actually this minus x square by 2, and this some function of f of y is actually y square by 2. So from this you can just simplify and write something like just add the missing function in either of the function and then write the final form of psi, that is y square minus x square by 2 plus xy plus some constant c. So the correct answer would be option D. Okay. Now let's look at question number 6. A stream function for a two-dimensional incompressible flow field is given by, I think I want to zoom out a bit. Psi is given as x cube minus 3x y square. Okay, psi is already given. You need to find the velocity field. So this again gives you a brief idea like why stream function is important. Like even by only knowing the stream function for a 2D incompressible flow field, you know the entire flow field now, right? Because this will give you the velocity components. But rather, if the very definition of stream function was non-existent, you had to solve for u and v separately by incorporating the momentum equation. That would have been a tedious task. But rather now, since you know stream function, you know the velocity field itself, because you're by only knowing the one function or one variable, you know the entire velocity field. Okay. So again, these things are easier to be said than understood at the first explanation. So I think it's better if you just try to understand the concepts by reading it again and again. That would be great. Okay, you know psi, so we can just use the relation u is equal to dou psi by dou y and v is equal to minus dou psi by dou x. Then we can find the velocity components. So the viewers of the video might pause it now and then just compare with my answers. Okay, so I will show the answer now. So we have u is equal to dou psi by dou y is equal to minus 6xy, and v is equal to minus dou psi by dou x minus 3x, that is minus 3x square plus 3y square. Okay. Then just substitute the value of 1 and 2 in this equation. So we are asked to find the velocity field at 1 and at this coordinate 1, 2. Okay, so just substitute the value of x equal to 1 and y equal to 2. So you will get something like u is equal to minus 12 and v is equal to 9. So you will get the velocity vector v is equal to minus 12 I cap plus 9 j cap. Okay, so let us look into the final question. I hope this is clear. Okay, so the final question is, for a two-dimensional rotational flow, the velocity potential is given by phi is equal to minus x square plus y square. Okay. Now this is a interesting question. So you need to find what is the corresponding value of stream function psi with the condition that psi is equal to 0 at x and y equal to 0. Okay. So from the given velocity potential, you need to find the corresponding value of stream function given that psi is equal to 0 at x and y equal to 0. Okay. So first thing would be to find the velocity components using the definition of the velocity potential, that is u would be equal to dou phi by dou x and v would be equal to dou phi by dou y. Now once you get u and v from using the definition of velocity potential, again just use the velocity of stream function to find the value of psi from the definitions of u and v. Okay, and then use this condition to find the integration constant c and just compare your results. Okay, so let us look into it, how we have solved it. So you get, from this equation you get u is equal to dou phi by dou x using the definition of velocity potential. So u is minus 2x. Okay. Similarly, v is dou phi by dou y, or v would be equal to 2y. Okay. Very simple derivation. Now you need to find the stream function using this relation. So you have dou psi by dou y equal to minus 2x and dou psi by dou y to be equal to minus v, dou psi by dou y equal to minus 2x and dou psi by dou x is equal to minus v dt is equal to minus 2y. So psi would be equal to minus 2xy plus some function of x, and psi here would be, if you integrate it, you will get psi equal to minus 2xy some function of y. So you can see that since these two are explicitly equal to each other, then our stream function using the similar argument that we did in the previous discussion. So since, just to say, since these two are exactly the same and f of x, there is some function of x and some function of y, then you can assume that these two are equal to each other and equal to 0, because there is no additional difference in this definition of psi. And there is a, of course, integration constant c. Okay. Now it is given that psi of xy is equal to 0 at x equal to 0 and y equal to 0. So it implies that psi, from, if you substitute the value of x and y in this equation, psi will be equal to 0 to be and which will be equal to c, because x and y equal to 0. So it implies that c is equal to 0. So you get your psi x of x and y to be equal to minus 2xy. Minus 2xy. Okay. So if you compare this to your given options, so the correct answer is option B. Okay. So I think yeah, that's all for today from my side. But I think today's discussion might not be that conceptually, I would say not analytical or calculation wise heavy, but I think conceptual wise it might become very, very heavy if you just look into the depth of it. Okay. So the importance of stream functions and velocity potential are very, very useful, and you will see that eventually we'll discuss or get back to the definition of velocity potential when we discuss the potential theory. Okay, the potential flow theory. So then I won't reiterate how it is defined and why it is useful. Maybe you can, if you revise it properly, you will be able to understand those concepts very clearly. Okay. Stream functions also, I think it might be revisited in the later part of the course. So it's especially in the boundary layer theory. Actually, like when we discuss the boundary layer theory, sadly I don't think we will discuss very thoroughly the boundary layer theory, which is actually a very interesting topic. But the solution of boundary layer theory are also sometimes take the use of stream functions. Okay, so let us see. I don't think we will use it now, but okay then. Let us end today's class and let's all meet next week. Okay, so have a nice day, have a nice week ahead, and take care.